Let us see section B. Question 15 and 16 are case study based questions and are compulsory. Attempt any 4 sub parts from each question. Each part is of 1 mark. So 2 questions, 8 marks. Look the question number 15. An electron, proton and neutron moving parallel to each other in the same direction with equal momenta. When all of them enter a uniform magnetic field which is at right angle to their velocities, a magnetic force F equal to QV cross B act on them, due to which they follow different tracks. This is the paragraph. Based on this paragraph, whatever you have learned in the topic, 5 sub parts of the question are given here. This is 1, 2, 3, 4, 5. You have to attempt any 4 parts correctly and 4 marks will be awarded. Let us see the first one. Looking downwards, an electron appears moving anti-clockwise in a horizontal circle under a magnetic field. The direction of magnetic field is, look, you know the force acts on a charged particle moving in the magnetic field, that is called Lorentz force. What is the formula? It is given in the para, this F equal to QV cross B. This force is on the positive charge moving with the velocity V in the magnetic field B. What you have to do? It is given electron appears moving anti-clockwise in a horizontal circle in a magnetic field. You know, left hand rule, this Fleming's left hand rule gives the direction of force acting on the moving charge in the magnetic field. Horizontal circle, electron is moving, this force is centripetal force acting towards the center of the circle. We have seen the motion of the charged particle when it is perpendicular to the magnetic field. When it enters perpendicular to the magnetic field, its path becomes circular. The anti-clockwise means, suppose in the horizontal circle, I am showing this is the clockwise and this is the anti-clockwise. Clear? Look, I am rotating my finger anti-clockwise. What will happen? Looking downward, this is the anti-clockwise direction. Then at any of the point of the periphery, suppose at this point my finger is coming in this direction. This is the direction of velocity. Look again at this point, this is the direction of velocity. Then if you keep the finger here to show the velocity of the positive charged particle and this force towards the center, then this is the circle, this is the velocity, this force is towards the center. Then this is the direction of magnetic field, but for which particle? Positive. Then for positive charged particle, tangentially at this point, if this is the magnetic field vertically downward, what will be the magnetic field's direction for electron, that is negatively charged particle? Vertically upward. So what will be the answer? Answer B. This will be the correct option. Okay. How to decide? You will have your own tricks. Okay. Look, second question. Path of a charged particle which enters a uniform magnetic field B at an arbitrary angle with the field direction will be. What happens whenever the magnetic field is given in this direction and a charged particle it moving with the velocity v in this direction? Then what happens? Its path becomes like this. It will move forward, as well as the component of velocity perpendicular to the direction of magnetic field B will make the path circular. Then this angle, suppose this is theta, then this is v sin theta and v cos theta. Learn, revise. So v cos theta gives the forward movement and v sin theta makes the circle. Then the forward movement circular path, this is the helical, like a spring. So what will be the correct option here? B, helical. third, work done by electron and proton will be. Options are given: electrons work done more than proton, less than, 0, none. You must be knowing, when the path is circular, motion of electron or proton in the magnetic field is the circular path, and there will be 0 work done. Why? Because work done is force dot displacement. Force and velocity will be perpendicular. Force and displacement will be perpendicular to each and every point of the circle. Therefore, no work done. So, this option will be correct. In the inward uniform magnetic field, the path of electron and proton will be. What I told just now in the first part, how to decide. Suppose this is the inward direction of the magnetic field, then you can see that the electron and proton, they will move at the circular path. Okay, how will you decide? As per tracing, how will you decide? Look that electron, suppose these are the two particles, okay, and this is given like this, and here it is given like this. This is the tracing given. This is an clockwise, and this is anti-clockwise. Which type of magnetic field is given? Inward. Which particle is electron, which particle is proton? You have to decide as per the options given here. Because both will move on the circular path, both are the charged particle. How will you decide? Similar explanation as in the first part I have given. Look here that this is the magnetic field. Okay, at this part, suppose this is the magnetic field, and the thumb is in this direction towards the center. So thumb is towards the center, magnetic field is inward. Then this is the motion of the positive charge. So this is the motion of the positive charge, not in this. Look at here at this point. Then how will you decide which one is for positive and which one is for negative charge? Look here. What will be the answer? B. Proton anti-clockwise, electron clockwise, as per the Fleming's left hand rule. Last option, this last part, last 5-1, the radius of the circular path will be. Look, in the para it is given, they are moving with equal momenta. And you know what is the radius formula, radius of circular path? mv upon qb, and this mv is called momentum. So momentum for both the all the particle is same. Therefore, charged particles are electron and proton. Their radius of the circular path will be same. Which option is correct here? Again B. So in this way, many questions can be framed. Out of them, you should know the correct answer with proper understanding and deep knowledge of the particular part of the portion given. Look the second question, 16th one. See the question 16 of section B. When photons of energy 4.5 eV are incident on metal surface 1, the ejected electrons have stopping potential V1 and de Broglie wavelength lambda 1. When photons of energy 4.7 eV are incident on another metal surface 2, the ejected electrons have wavelength lambda 2. Given lambda 2 equal to 2 lambda 1, these electrons can be stopped by potential minus V2, and V2 is given by V1 minus 1.5 V. Questions again, 5 subparts based on this paragraph. You know what is this photoelectric effect? Basic equation of photoelectric effect, you know, when the incident photons have energy E, suppose EI incident, and this energy is, when photon is incident on the metal surface, then partly used to take out the electron from the metal surface. This is work function. It is also denoted by phi or work function W in some books, plus rest of the energy is provided as the kinetic energy to the electrons. This is the basic equation of photoelectric effect. Now see the questions. You have to do any 4 parts. 1 part 1 mark each, so total marks are 4. See the first part. Stopping potential is the measure of. Stopping potential is that negative potential of anode due to which any of the maximum kinetic energy electron which is emitted by cathode cannot reach to it. So stopping potential is the measure of maximum kinetic energy of the emitted electron. Which option? Incident energy, maximum kinetic energy of the incident. So this option will be correct. Second question, photoelectric emission is possible when? Just now we have seen incident energy is greater than work function of the metal, less than work function of the metal, frequency of incident photons less than threshold frequency, large number of photons are incident on surface for very long time. Look, if you have clear-cut concept of photoelectric effect, then electrons are emitted from the metal surface only when the incident photons have energy greater than the work function of the metal surface. So this is the correct option. Third, the stopping potential V1 is equal to. Now look, go to the para. It is given V2 equal to V1 minus 1.5 volt. Also the de Broglie wavelength, it is lambda 1 for first surface and lambda 2 for second surface with this relation. You know, it is given lambda 2 equal to 2 lambda 1. And what is de Broglie wavelength? You know, de Broglie wavelength is h upon p, and p can be written as 2mk. You know, momentum under root twice of mk. So for 2 you will write here k2 kinetic energy. Here you will write 2 into h Planck's constant upon 2mk1. What will you get here? Whole square. This will be 2 here. This will be 4k2. So this k1 equal to 4k2 will be or not? This 2m will be cancelled. K1, you know, electron volt is the unit of kinetic energy. So you can write here this E1 is equal to 4 eV2. That means V1 is 4V2. So in place of V2 you can write V1 by 4. Look, this is the expression given. Then V2 equal to V1 minus 1.5 gives you V1 by 4 equal to V1 minus 1.5. This implies that this 3 by 4 V1 equal to 1.5. Therefore V1 equal to 6 by 3, that is 2 volt. Which option will be correct here? This one. How to solve the question you have seen. See the next one. The kinetic energy of electrons emitted from the metal surface. Look, how will you solve this part? Again we have seen that V1 equal to 2 volt. Kinetic energy of the emitted electron. How? From the metal surface 2. For the metal surface 2, if you write the expression for photoelectric effect, then you write here this is kinetic energy 2 and this is incident energy for the metal surface 2. What is the metal surface energy incident photons? Is 4.7. So you put here this is 4.7 EV equal to this work function phi 2, or you can write with the symbol this phi 2 plus kinetic energy this KE2. You know, the kinetic energy emitted from metal surface 2 can be obtained with the help of this. How will you find this 4.7 EV, and what was this K2? K2 was K1 by 4. So if you see that the K2 is K1 by 4, and from this relation V2 equal to V1 minus 1.5 V, what will be K2? K2 will be EV2, and what is V2 given here? We obtained from this V2 is V1 by 4. We have got here relation V1 is 2 volt, V1 by 4 is 0.5. So this is E by 2 V. 0.5 means half V. Look again, since V2 equal to V1 minus 1.5. What is V1? 2. So 2 minus 1.5 is 0.5 or half volt. So K2 is half EV. Put here 4.7 EV minus this 0.5 EV, half is 0.5, this will be equal to work function. So this work function is calculated, then 4.2 EV. Stopping potential V1 equal to this V1 equal to 2, this fourth part, kinetic energy of electrons emitted from metal surface. So it is only, we have to get this one. What is the kinetic energy? Half EV. You know this half EV is the maximum kinetic energy. Look here, this is the option given half EV, but read the other option too, between 0 to 0.5 EV. Which option you will mark correct? This one, because this is the maximum kinetic energy and you are calculating here this maximum kinetic energy from the equation. So this option will be correct. Now the work function of metal 2. How will you find the work function? Initial is 4.7 EV minus kinetic energy is 0.5 EV. That will be the work function for metal surface 2. What will be this? 4.2 EV. So this one will be the correct answer. In this way, you have to solve the questions.